One of the most delightful papers I have ever read was written by Witten in 1982, the year of my birth. In it, he discovers what is now called the bubble of nothing. And one of the ways you can tell it's such a great paper is that after being discovered by Witten in the early 80s, it was independently rediscovered in the late 90s. And by doing a literature comparison between the two of them, you can really appreciate the elegance and brevity of the Witten discovery. What is it? The bubble of nothing is an instability of 3 + 1 dimensional Minkowski times S1 with a uniform extra dimension with just Einstein gravity. And the instability is a cataclysmic decay in which space-time pinches off. So here's a snapshot of 3 + 1 dimensional Minkowski cross S1, a constant time snapshot, and here's an extra dimension. And if you go up here, you reappear at this side. And the decay is a non-perturbative decay in which space-time pinches off. The size of the extra dimension smoothly goes to 0 in a certain three-dimensional region. So you end up with a ball, a three-dimensional ball, in which there is no longer space-time. Because the size of the extra dimension that was, say, 1 centimeter, a very, very long way away, smoothly, following this function, approaches 0, a finite distance away from the origin, with a finite area radius away from the origin, with that area radius, the characteristic size, being set by the scale of the extra dimension at infinity. So this is the non-perturbative decay, and it's called a bubble of nothing because the idea is that in here, there's now an excluded region. If you took a balloon and put it around this region and contracted that balloon, there'll be a minimal size. In fact, that's what it looks like at the instant of nucleation. It then grows, accelerating outwards and approaching the speed of light. So the excluded region gets larger and larger and larger, and inside we say there is nothing. However, this space is geodesically complete, and it's also got the 5-dimensional curvature scale is never higher than the scale of the extra dimension. It's never shorter distance scale than that, so this is a perfectly smooth space. It's just one that smoothly pinches off. So, as well as describing the process, Witten calculated the rate, and the rate goes like e to the minus L squared over h bar g, L being the size of the extra dimension. So as L goes to infinity and you recover 5-dimensional Minkowski space, this means that the space becomes completely stable, which is required by the positive energy theorem. But for finite L, the rate is small but non-zero. The other thing to notice about this rate is that it goes like e to the minus 1 over h bar. This is a process that is non-perturbative in h bar. And e to the minus 1 over h bar is in fact characteristic of quantum tunneling processes. You know from one-dimensional quantum mechanics that if you want to tunnel through a barrier, the rate goes like e to the minus 1 over t. However, you also know from one-dimensional quantum mechanics that there's another way to get across a barrier. The other way to get across the barrier is to heat up whatever system you're looking at, and then there'll be a non-zero probability that it'll fluctuate to the top of the barrier rather than tunneling through. And that rate, rather than being non-perturbative in h bar, is non-perturbative in t, e to the minus 1 over t. So, a motivating question for this talk is the same true for bubbles of nothing? As well as being able to make them by the Witten process that goes like e to the minus 1 over h bar, is there also a thermal process that makes them that goes like e to the minus 1 over t? And the answer to that question, I will reveal, is yes. In fact, there's another question, which is it possible to do some hybrid process where you fluctuate partway up the barrier? This is just some sort of conceptual barrier now. You fluctuate partway up and tunnel the rest of the way, and the answer to that question will also be yes. So what are we really asking here? The question we're really asking is, what are the decays of hot KK space? This is a decay of KK space at 0 temperature, but there are also decays if you add, this is an additional decay if you add a finite temperature. So that is going to be the question that we're going to address. What are the non-perturbative decays of hot KK space? And to be clear, we're in pure Einstein gravity. We're just going to take 5-dimensional Einstein gravity on R31 cross S1. So the perturbative impact of the finite temperature is to fill space-time with a thermal gas of gravitons. But the non-perturbative impact will be these various destabilizations. So if we didn't have a temperature and we didn't have an extra dimension, then we'd be stable. We'd be in 5-dimensional Minkowski space. You know that if you add a compact extra dimension, even at t equals 0, then you get the Witten bubble of nothing, the quantum bubble of nothing. I've promised you, and I will later show you, that at non-zero temperature, with a compact extra dimension, you in addition have the thermal bubble of nothing. But that's actually not it. There are actually further instabilities above and beyond just the bubbles of nothing. And to approach them, I will start by examining this square. So I will have no extra dimension now, and just look at the destabilizing impact of having a non-zero temperature. So first of all, look at the decays of hot space. And this is a story that goes back, again, to another great paper from 1982, Gross, Perry, Yaffe, who looked at what happens to 3 + 1 dimensional Minkowski space at finite temperature, full of a thermal gas of gravitons, and it has a non-perturbative instability to nucleate a black hole. Hawking told us that black holes have a temperature proportional to h bar and inversely proportional to r, which means small black holes are hot and large black holes are cold. And so for a black hole in a heat bath, if it's too small, it'll be hotter than the heat bath, it'll emit energy, get hotter, and soon be reclaimed by the heat bath. Conversely, if it's large enough, it'll be colder than the heat bath, absorb energy, get colder still, and grow forever. There's a critical black hole that's at exactly the same temperature as the heat bath, is in unstable thermal equilibrium with the heat bath, and that is the critical black hole that controls the decay of hot, flat space. We can be more quantitative. We can ask about the free energy of a black hole of mass r and black hole of mass m and radius r in a heat bath of temperature T. And the free energy is given by this expression. You get punished because of the mass of the black hole, proportional to r, but you get rewarded because of the entropy of the black hole, proportional to s squared. And so the free energy has a barrier, and sitting at the top of the barrier is a black hole that's in thermal equilibrium with the heat bath. And so the rate is to decay is just the rate to the Boltzmann rate to fluctuate a black hole that's sitting at the top of the barrier, e to the minus the free energy of that black hole divided by the temperature, which is given by this expression. Let me just very briefly say that there is an addition of perturbative instability of this space-time, which is the Jeans instability responsible for the existence of the Earth, but we can banish that instability because it's a very long wavelength instability. It's a very IR instability, so putting any IR cutoff will kill those modes without affecting these.
So doing exact expansion of the universe, which is generated by this.
That's right. So there's a Jeans instability, there's a Hubble length, there's a whole bunch of, if you like, perturbative instabilities, all of which have this length scale. This is also the Hubble length scale. So, for example, by putting an IR cutoff, your favorite might be an ADS length that's much longer than this length and much shorter than this length. Then you'll get exactly the Gross-Perry-Yaffe story without having to worry about those. Okay, so we're now starting to fill in this square. With no extra dimension at t greater than 0, we have a black hole. And actually, there's a cousin of the black hole that exists at t greater than 0 when there's a compact extra dimension. Because now we're in 5 dimensions, there's actually 2 possibilities. We can make a black hole or we can make a black string. The black string uniformly wraps the extra dimension. The black hole lives inside the extra dimension as a 5-dimensional black hole. It's called a caged black hole in the literature. Caged, the idea is that the compact extra dimension forms a cage. Okay. And which one of these wins? Which one of these two, the 5-dimensional black hole or the 5-dimensional black string? Which one of those two wins depends on the temperature. If you move from colder to hotter, then the black string gets fatter and the black hole gets bigger. And there's a couple of interesting things that happen. If you get really, really hot, then nothing weird happens to the black hole. It just gets very small because size is inversely proportional to temperature. But eventually the black string becomes so thin that it has a Gregory rule of Flamm instability. It picks up an extra negative mode. It's still a solution to the equations of motion. It just no longer has the it now has two negative modes, not just the thermodynamic instability because of the heat bath, it also has a mechanical instability to become inhomogeneous in the extra dimension. At the other side, nothing peculiar happens to the black string when it gets cold, it just gets fatter and fatter and fatter, but the black hole eventually is too large to be contained within the extra dimension. So it collides with itself in the extra dimension, and it no longer exists as a solution to the equations of motion. Which one of these wins is going to depend on the temperature? The black string, we just have an analytic formula for what its free energy is. The black hole, when it's really, really tiny, we just have an analytic expression for what its free energy is. It's just the free energy of a five-dimensional black hole. But at finite temperature, it picks up corrections that can be calculated in a perturbative expansion. The leading correction lowers the free energy, and you can understand that as a result of the attraction of this black hole to its image black holes. There's an array of image black holes, and it's attracted to them. So it's moving down into a gravitational potential. It has lower free energy than you thought it did at fixed asymptotic temperature.
What problem is really being solved here? So if the black hole is very small, then I guess you just impose those boundary conditions. But really, you're imposing the boundary condition is far away?
All the boundary conditions are infinity. At infinity, I'm fixing the asymptotic temperature and fixing the asymptotic size of the extra dimension. And then as I go in, I'm going to fill in however it fills in. Okay, so now we can plot these, and people have done complicated numerical calculations, figuring out what the free energy of all these is. If I plot, so I'm asking for the free energy of a black hole or a black string in thermal equilibrium with a heat bath of asymptotic temperature T. And if I plot T squared F, then that kills the leading order contribution for the five-dimensional black hole. So this is just for the caged black hole, it's just a horizontal line. It's independent of T, the free energy, except it bends down slightly because, again, of the attraction to the image black holes. I can also plot the black string on this diagram. And there's at low temperature, the black string is fine, but at very high temperature, it undergoes a Gregor-Laflamme instability and picks up an extra negative mode. And so which one of these wins in the decay rate, since the decay rate is e to the minus the free energy divided by the temperature, which one of those wins depends on the temperature? At low temperature, the black string wins. At high temperature, the black hole wins. You want to have as low a free energy as possible. So that is the answer to that question. Let me also mention that there is another solution, which is the lumpy black string, which is it never contributes to the decay rate, but it's another solution with an extra negative mode. It's the inhomogeneous black string, and within this phase diagram, it mediates between those two decays there. Okay, so this is the answer to the question we asked. What is the decays into black holes and black strings of hot KK space? And depending on the temperature, either the black string dominates or the black hole dominates. Right. Okay, so that's the black holes and the black strings. That's the Gross-Perry-Yaffe story sort of improved with by adding an extra dimension, made more complicated by adding an extra dimension, and that's the answer. Are there any questions about that before I move on to the next part? Okay, well, so bearing that in mind, before I talk about bubbles or nothing, let me talk about quantum mechanics again. Let's just return to this question of one-dimensional quantum mechanics and about finite temperature tunneling in one-dimensional quantum mechanics. And what we're going to do is we're going to pedantically look at this particular case, because it's going to turn out that this very simple case is going to have all the features that the bubble of nothing is going to inherit. So let's ask, what is the rate in the semi-classical approximation to fluctuate from x equals 0 to x equals x bar, to thermally fluctuate there, and then quantum mechanically tunnel the rest of the way and decay in that manner? What is the rate of that as a function of where I choose to fluctuate to, as a function of x bar? There are two contributions to the rate. There's the Boltzmann suppression that punishes you for fluctuating a long way up, because it costs you more Boltzmann suppression to fluctuate a long way up. And there's the WKB tunneling term that rewards you for fluctuating a long way up, because then you've got less far to tunnel through. And what is the optimal x bar to choose? What's the best place to fluctuate to? is going to be determined by the interplay of these two terms that are acting in opposition to one another. And so when you calculate this quantity, that will be the same as calculating the e to the minus the Euclidean action of the corresponding instanton. And so which one of these two wins, the Boltzmann suppression or the WKB suppression, is going to depend on the temperature. At very low temperature, you're very heavily suppressed for fluctuating all the way up. And so the Euclidean action is a monotonically increasing, or almost monotonically increasing function of x bar all the way up to the top, which means that the tunneling rate is a decreasing function of x bar. So at very low temperature, you just want to fluctuate up a tiny bit before tunneling the rest of the way. At very high temperature, now the Euclidean action really is a monotonically decreasing function of x bar. It's very high temperature, so you just want to fluctuate all the way to the top, and that's the optimal value of x bar, and also therefore the fastest way to traverse this barrier. At intermediate temperature, you can get some peculiar intermediate behavior, where there are now two local minima of the tunneling rate with regards to x bar. There's a local minima that jumps a little bit and then fluctuates the rest of the way, and there's also a local minimum of the tunneling rate, a local minimum of the Euclidean action, therefore a local maximum of the tunneling rate that goes all the way to the top, and these two exchange dominance in a first-order phase transition.
So normally we just compute this Euclidean instanton. If it's at finite temperature, then Euclidean time is periodic.
Great, that's a good question. Let me come back to that in a moment. Okay, now I'm ready for it. So what we want to do is we want to look for the minimum of this function with regards to x bar. And so now I can solve some equations, and by differentiating this rate with regards to x bar and putting it equal to 0, I will find that doing that, if I then consider that'll pick out those three places as the only three locations where the Euclidean period is equal to beta. So in this way of saying things, by imposing that the Euclidean period is equal to beta, you are automatically picking out the extrema of this function. So that's the sort of backwards way to say it from the normal way to say it, where you just impose the Euclidean period to be beta at the start. Mm-hmm. Physically, what you're doing when you do that is you are choosing the extrema of this function. You're picking out the optimal values of x bar from the start. Okay, so let's assemble this into a phase diagram of tunneling instantons at finite temperature. At very low temperature, the one with a minimum Euclidean action is the thermally assisted quantum tunneling. In fact, at very low temperature, you don't even get very much of a thermal assist. It's almost all quantum tunneling. At very high temperature, the one that wins is the purely thermal tunneling process that tunnels, that just goes all the way to the top and doesn't have any quantum tunneling at all. And then in the middle, you get a slightly more complicated thing going on, where, let's say, the pure thermal tunneling at some stage goes from having a positive, it's always a solution, but does it have a positive, it's always an extremum, but is it a minimum or a maximum? Does it have a positive or a negative second derivative? And at some stage, at low enough temperature, it picks up an extra negative mode. And similarly, for an intermediate regime, there's this terrible behavior where you never want to, where this is the absolute worst possible choice of x bar, the absolute slowest possible choice of x bar you could have chosen to traverse this barrier. And furthermore, at high enough temperature, the thermally assisted quantum tunneling process goes away entirely. That's something you can prove, which is, for people who know about telling this story in de Sitter space, that would correspond to the point at which the Coleman-de Lucia instanton ceases to exist, and there's only the Hawking-Moss instanton left. Okay, and then so this is the story in quantum mechanics. You get almost exactly the same story if you move from quantum mechanics to quantum field theory. So that was first derived by Linde in 1981, and you end up with thermal instantons that are uniform in Euclidean time, or quantum instantons that are non-uniform in Euclidean time. So it looks like and which one of those wins has some phase diagram that looks exactly like that. Okay, so this should look very familiar by now. this diagram, even though it's apparently talking about quantum and thermal tunneling and not about black holes. So what's going on? Particularly, if I draw these two side by side, you'll see that they have exactly the same structure. Only one has high temperature at this end, and the other one has low temperature at that end. And now I'm going to explain that. Are there any questions? Okay, so what is going on is that there's actually a high temperature, low temperature duality here. We are asking, you will recall, about the decays of hot KK space. So to answer that question formally, we should be looking at instantons that have not one but two compact Euclidean directions. One compact Euclidean direction is from the fact that there is a finite temperature, and therefore Euclidean time should be periodic with period beta. The other compact extra dimension is from the fact that we just literally have a compact spatial extra dimension of length L. And so we ask, when we're doing the instanton calculation, for the ways to fill in those asymptotics in the center to give me classical solutions that have one extra negative mode. And there's actually not one way to do that, there's two ways to do that. If you like, there's the black hole way to do it and the black string way to do it. So the black string instanton is just the Euclidean black string. It's the metric you get when you continue t to iw in the Euclidean to produce a Euclidean solution that asymptotically has two compact directions, and that instanton controls the decay of this space-time for some range of parameters. But the point is that this has two different, because there's two S1s, there are two possible analytic continuations of this instanton. This one instanton does double duty, controlling two different decays. There's a picture of the instanton. The two different decays it controls are the black string instanton on the one hand, and if you continue W, you just get back a black string. On the other hand, if you continue Z to IT, you get a solution that's a bubble of nothing solution, because now the extra dimension is pinching off. But unlike the Witten bubble of nothing solution, it's not a solution that's accelerating. It just sits there forever. It's static. Or rather, it sits there forever until you ping it, but actually, because it's sitting at the top of some potential barrier, it's actually sitting there in unstable mechanical equilibrium. So if you ping it, it'll either collapse down to zero size or expand forever. And so this one instanton controls those two decays. Similarly, there's a Euclidean black hole instanton, and that instanton again controls two decays. If you continue W, you get back a black hole, and if you continue Z, you get back a quantum bubble of nothing. And so this explains what we had in the last slide, why those two diagrams looked the same, because they are actually related by a high temperature, low temperature duality. That high temperature, low temperature duality comes about from the fact that you have the same instanton that you're just continuing in two different ways to get two different decays. Since you reinterpret, in one instanton you interpret let's say the black string instanton, if you interpret this direction as space and this direction as time, then space pinches off but not time, and you have a bubble of nothing. If you interpret this direction as time and this direction as space, then time pinches off, Euclidean time pinches off, that means you have a horizon, and you have a black string, therefore. So in flipping this interpretation of these instantons, you're flipping the periodicity of what used to be the periodicity of time becomes the periodicity of space, and what used to be the periodicity of space becomes the periodicity of time. In other words, you're flipping beta goes to L and L goes to beta. In other words, this is a high temperature, low temperature duality relating beta to 1 over beta, and it's a duality that therefore unites the Gross-Perry-Yaffe story with the Witten story. the Witten story is about bubbles of nothing, the Gross-Perry-Yaffe story is about black holes, but there is a high temperature, low temperature duality that relates them. The quantum bubble of nothing, the Witten bubble of nothing, is related to the black hole, and the thermal bubble of nothing is related to the black string by this duality. So for one of these space-times at a given value of beta and L, you're going to find that it has these four possible decays. If you flip beta and L, it still has four possible decays. Those four possible decay rates are all still the same, but the identities of those decays are now permuted. What used to be the rate to decay to a black hole becomes the rate to decay to a quantum bubble of nothing, and vice versa. And so, in fact, we can now be precise about that. Here's the rate to make a thermal bubble of nothing. A bubble of nothing by thermal means. Here's the rate to make a black string, a four-dimensional black hole, a five-dimensional black string. And you get from one to the other just by flipping beta and L. Similarly, here's the rate to make the five-dimensional black hole, which you can calculate in a perturbative expansion in beta over L. That also gives the rate to make a thermally assisted quantum bubble of nothing, whose leading behavior is independent of beta, and then has a perturbative expansion out there. And so you can plot those all on one diagram, and here's what it looks like in 3 + 1 + 1 dimensions. The whole diagram is symmetric around the self-dual point, is symmetric around beta over L, and these are all the possible decays of hot KK space. I've removed some of the ones that have extra negative modes just to make it easier to see. At very high temperature, the five-dimensional black hole wins, though there's a first-order phase transition to black strings in the black string sector. At low temperature, the quantum bubble of nothing wins. So actually, in 3 + 1 + 1 dimension, even though there's four possible decays, only two of them ever dominate: the black hole or the quantum bubble of nothing. That doesn't mean that the others are uninteresting, because they lead to different places, but the globally dominant decays are only ever two of them, separated by beta over L. In higher dimensions, that actually no longer becomes true. In higher dimensions, if you go for Rn1 cross S1, you'll find that there are regimes of parameter space where all four of them dominate. And so one of the nice features of this is this duality here and this perturbative expansion here. It would be really hard to calculate what the you know the exact quantum bubble of nothing, because that's just a five-dimensional Schwarzschild space-time. But these thermal assists to the quantum bubble of nothing will be extremely hard to calculate. Thankfully, you don't have to calculate it, because other people have already calculated it in the context of five-dimensional black holes, and you can just steal their result and then double analytically continue it, and also their numerical results. And so you have this nice feature. The five-dimensional black hole, with a finite size extra dimension, is easier to make than you thought it would be. It's easier to make than you thought it would be because it notices its image charges in the extra dimension and is attracted to them, and that lowers its free energy at fixed asymptotic beta and L. Similarly, the quantum bubble of nothing is easier to make than you thought it was going to be at zero temperature now. It's easier to make than it was at zero temperature, and the interpretation of that is simple. It's that adding a finite temperature can never hurt you, it can only help you. The way in which it helps you is you get a thermal assist, where you fluctuate a small way up and then tunnel through. And so this is a duality that relates one of the things this duality rates is how much faster it gets because of the thermal assist to how much faster you get because of the attraction to your image charges for the black hole. And then everything else maps across too. The negative modes map across. The mechanical instability of the thermal bubble of nothing that's just sitting there ready to expand or contract is dual to the thermodynamic instability of a black string in a heat bath. So recall the Gross-Perry-Yaffe story. There's a story where if you have a small black hole, it falls down to zero size. If you have a large black hole, it grows forever. And there's a critical black hole in the middle that's just right in thermal equilibrium with the heat bath and has an extra negative thermodynamic mode. That story has an exact analog for bubbles, where if you have a tiny bubble, the surface gravity will seal it up. If you have a large bubble that's larger than the Coleman bubble, it'll grow forever because the pressure will beat the surface tension. And this duality makes that means those aren't just a bit analogous, they're actually exactly the same thing. And then you can look through all the other points, and they all have some other interpretation. For example, the Gregory-Flam instability that sets in for the black string is dual to the point when the purely thermal tunneling picks up an extra negative mode. What in de Sitter space would be the point at which the Hawking-Moss picks up an extra negative mode is dual under this duality to the Gregory-Flam instability. Okay, so that's the answer. What are the decays of hot KK space? There are a total of 4 decays, one of which is operative even if you didn't have the extra mention, one of which is operative even if you didn't have zero temperature, and 2 of which rely on both. Even though there are 4 decays, there are only 2 Euclidean instantons, because each Euclidean instanton does double duty. And because each Euclidean instanton does double duty, there is a high temperature, low temperature duality that relates across that way and that way. And the reason I really like this story is that it sort of unifies this Gross-Perry-Yaffe story with the Witten story, both papers from 1982. Okay, so what is the moral of this? If I were to have a take-home message, it's that quantum gravity, we have learned, is hard, and we need all the help we can get. The black hole is a very simple toy system from which we've learned a very great deal. The bubble of nothing is also, the nucleation of bubbles of nothing is also a simple semi-classical quantum gravity system from which we perhaps still have a great deal to learn. And what I'm doing at the moment is I'm thinking about the entropy of a bubble of nothing and asking whether we can consistently assign an entropy to a bubble of nothing. And the answer to that question seems to be yes, and that it's negative. Okay. You'll have to wait for my next talk.
Saying no when it's positive? Not a duality.
Okay, I'm coming under time. Are there any questions?
Is there a larger SL2Z?
Great question. As far as I can tell, the answer to that question is no. So asymptotically, we have a rectangle when I'm calculating these instantons, one of which has size beta, and one of which has size L. And what I've done is I've considered, say in the black string case, a black string that wraps that way is a black string, and a black string that wraps that way is a thermal bubble of nothing. And so there are 2 things you could ask about. You could say, one question you could ask is, well, what happens if I turn on an angle and do that? And the other question you could ask is, what happens if instead of doing this, I do that? Okay, so if I didn't have it to analytically continue it, there would be an SL2Z symmetry, and everything would work out perfectly. There'd be an infinite family, discrete family of solutions like this. Let's say I had a T2 extra dimension. I could ask about bubbles, so rather than an S1 extra dimension and finite temperature, I could just take a straight up T2 extra dimension. I could ask about black strings that I nucleated that wrap any cycle you like. This one, that one, any of these. The complication that I've had in trying to extend this to SL2Z is that you can't just write this down as a Euclidean solution and declare victory. You need to analytically continue it to a Lorentzian solution that has the appropriate properties. And it seems as though these just give nonsense. They have, it gives you complex metrics with conical singularities, and I haven't been able to make any sense of it whatsoever, and I'm coming to the conclusion that these just don't have any physical interpretation.
There's a Euclidean solution with these asymptotic boundary conditions.
There are absolutely real Euclidean solutions with these asymptotic boundary conditions. That's pretty much guaranteed by the SL2Z symmetry of everything. You can definitely write them down. The question is, do they have any physical interpretation, or are they just, do they not mean anything? And as far as I can tell, they don't mean anything, because you can't continue them to Lorentzian spacetime. These, I will quickly mention, do have a meaning. The meaning of these is when you've turned on a Kaluza-Klein chemical potential. So there are two rest frames, Lorentz rest frames, in the X dimension. You can boost in the X dimension, but there are two things that break that symmetry. One is the rest frame of this thermal gas of gravitons that has some preferred rest frame in the X dimension. The other is the fact that you've done an identification picks out a preferred topology. The topology picks out a preferred rest frame in the X dimension because it's the twins paradox on a cylinder, and there's some preferred frame in that X dimension. And what theta corresponds to is there being a rapidity that separates those two. And then these two make perfect sense. This is nucleating a black string that's not at rest with respect to the N dimension, but is moving around the X dimension. And this is some thermal bubble of nothing that also exists. So that story makes sense, but I think these just don't make any sense whatsoever.
Okay, so there's a souped up version of this story where you have not only finite temperature but also finite angular momentum.
Yes.
In the extra direction, and
that's right. And then the story all makes sense, and you can calculate the decay rates this way, or you can calculate them by calculating the free energy when you include a chemical potential, and all of those answers are consistent and give you what you'd expect the answer to be.
Before you had beta over L goes to L over beta.
Yeah, now
you have J or whatever, some chemical potential.
Yeah, now you have theta, so there's now a slightly more complicated expression, but it becomes beta cosh eta, where eta is the rapidity, over L goes to L over beta cosh eta.
Are the SL2Z ones things that look like they would contribute or dominate if you were working in Euclidean signature at imaginary chemical potential?
No, yeah, so theta isn't really the chemical potential here, it is the imaginary chemical potential is what you'd have to say. And yeah, so you end up, I mean, there is a step where you take theta goes to I times the chemical potential. Yeah, as Euclidean solutions, they do everything makes sense. It's only when you try and Lorentzian continue them that you get nonsense. So.
And I'm just thinking about the SL2Z family of black holes in ADS, where those are the things that would dominate an ensemble with an imaginary value of the chemical potential for angular momentum.
Yeah, if you were willing to let your metrics all be complex, then I think you would.
Yeah,
there would be an instanton that you couldn't say there was anything wrong with it.
At the level of trying to interpret the Euclidean solutions, they're the things that would, different instantons dominate in different regions of parameter space, and they're the things that would be the dominant contribution at an imaginary value of angular potential. So just the physical interpretation, as you say, is a little unclear, though.
Yeah, I'd be inclined to say that these don't contribute to the decay rate, whatever they are, but I mean, there are closely related problems in which they do contribute to the decay rate, but in this continuation they apparently don't. So. Ted, did you have a question?
Would you be willing to say anything about the entropy?
Yeah.
Oh, okay. Well, this isn't really related to this train of thought, but right. Okay, so there is one of these bubbles of nothing that we can calculate the entropy of, and it's 0. That's the thermal made bubble of nothing, which looks different from the quantum bubble of nothing. The thermal bubble of nothing is the one that's dual to the black string, and you nucleate and it just sits there. That's like a bubble of nothing that's sitting at the top of the potential. And since it's static, we can...
It has zero mass.
It does not have 0 mass, no. Right, so in fact, these are its properties here. Because it has, right, so the Witten bubble of nothing does have 0 mass. If you're thinking about tunneling through some barrier, where R is the size or the area radius of the pinch-off of the X dimension, and V is, let's say, the ADM energy is here, then you can imagine that you have some barrier that looks like this, just like you would with a common dilution bubble. And the Witten bubble of nothing does have zero mass, and it just sits there. But it doesn't just sit there, it accelerates away. This is the thermal bubble of nothing, and it has all the properties that you'd expect from a diagram like this, which is to say it's smaller than the Witten bubble of nothing. It doesn't have zero mass, it has positive mass, and it does just sit there. If you don't perturb it, it'll sit there forever. It's a static
When you
solution.
say it has mass, do you mean somebody outside it sees a massive object?
I mean, it's got an ADM mass, that's right.
How did they get the ADM mass since it didn't have one to begin with before?
It took it from the heat bath.
Oh, it took it from the heat bath. Good.
Though actually, intriguingly, even though it does have ADM mass, it doesn't attract geodesic observers who are moving with no KK momentum outside it, because there's like a gravitational attraction to it, but there's a scalar repulsion from it, and those cancel out. So there's no force on it. The geodesics around it just move around. So for this thermal bubble of nothing,
That's a KK convective location, so it's this.
sorry, what was the question?
I was asking where the scalar comes from.
Yeah, the scalar is the radion. There's a radion repulsion from it. Things don't like to go to places where the extra dimension is small,
I thought
because
scalars can't make repulsion. I thought scalars always make attraction.
in this case you do. If you have something where there's an extra dimension that's pinching off, things don't like to go there. In any event, you can take the metric and calculate the geodesics, and it's definitely the case that there is no deviation towards or away from the black string. Okay, so in this case, the black string thermal bubble of nothing, that's not the one that I'm going to claim has an entropy. This has a calculably zero entropy. And it's quite fun the way it has zero entropy. You know that because of the duality, it's got to have the same action, or rather a dual action. At the self-dual point, beta equals L, it's got to have the same action as the black string, the thermal bubble of nothing. So the fact that it has the same action at the self-dual point means that it has the same free energy. So when beta equals L, the action is just equal to beta times the free energy for these things. So if we look at the point where beta equals L, these two have to have the same free energy. But the way that free energy is made up differently. Even though they have the same free energy, they have a different ADM mass. The black string is in fact twice as heavy as the thermal bubble of nothing. But it precisely compensates for that by having an entropy that's also large, so that the difference of those is the same. They have the same free energy. And so that's consistent with a thermal bubble of nothing having zero entropy, which makes sense, because the thermal bubble of nothing doesn't have any horizons in that space-time. It's just a hole that's sitting there, and if I want to talk to you, I can just walk around it at my leisure, and we can have a conversation, and then I can walk back. The same is not true for the Witten bubble of nothing. The Witten bubble of nothing is expanding. If you're sitting on the other side of the bubble of nothing from me, and I want to have a conversation with you, I try to walk around the bubble of nothing, but then the bubble of nothing grows. And in fact, it grows so rapidly that we can become causally disconnected. In fact, the causal structure of this space-time is just defined by the de Sitter space, the codimension 2 de Sitter space that lives on the bubble wall. So there are Lorentzian horizons. You might imagine that associated, even for geodesic observers. So an observer who's just sitting here on the bubble wall is following a time-like geodesic. Even for those observers, there are Lorentzian horizons, and you might think that there is an associated entropy.
Is it a killing horizon? There's a killing symmetry that generates.
There is the time-like killing vector of the codimension 2 de Sitter space. I'm not sure. There's a whole bunch of de Sitter spaces here, and you need to connect them. I think that might mess up the killing.
No, it's fine.
Is it fine?
Yeah, it's the Wick rotation, the rotational symmetry of the black hole.
Okay, great.
But are you saying that the entropy is independent of the time?
There is a time, not a global time-like killing vector, but there's a
No, it's not global time. But
Right.
does it make sense to talk about the entropy at a time?
I think you'd want to take those time slices relative to the de Sitter. If you took those time slices relative to the static patch on de Sitter, then it certainly would be independent of the time. If you wanted to do global time, I'm not sure what.
Yeah.
Okay.
Okay.
You're asking me about something I haven't written a paper about, rather than something.
It's killing writing. Its area is independent of how you cut it.
It's like
Well,
Okay.
that's a good place to finish. Thanks
Okay.
very much.